Hello students, this is Professor Fernetovich back with a video about chemistry for fermentation science. So chemistry might be something that you have taken recently as a college course, or maybe it was a long time ago since you last thought about chemical elements, atoms, and bonds. In either case, this can be a refresher for you or some really important information that you need to have. So we are going to be looking at chemical elements today, looking at atoms, subatomic particles, and isotopes. Hello students, this is Professor Fernetovich with a video on chemistry for fermentation science. Today we're going to be looking at chemical elements, atoms, molecules, compounds, and bonds. So for some of you, this may be a review of something you've recently done in maybe a chemistry course. For others of you, this might be ancient history, something you did in high school a long, long time ago. In either case, this is important information that will serve as a foundation for what we study with fermentation. We're kind of looking at the tiny part of things right now and then looking to expand on this as we go further in our studies. All food, in fact, everything around us is made of chemicals. So whether you're eating a grape or breathing air or sitting at a desk, you are interacting with chemistry. Chemistry is all around us. So everything in here is a product of various chemical reactions that happened either naturally or with the help of people. So the term matter is a technical term. It is a chemical vocabulary word. Matter is anything that has mass and occupies space. So mass is essentially weight. We can use those terms interchangeably for this class. And occupying space refers to volume, taking up space, three-dimensional space. Now matter can be living or non-living. So we are made of matter. And the desk that you are sitting at, or the chair you're sitting on, or the ground is made of matter. Even things we can't see, like the air, is made of matter. Now, matter, when we look at it, we can break it apart into 92 naturally occurring fundamental types of matter. And these are the 92 naturally occurring elements. So an element is a specific type of matter, and each element has its own properties to it. Okay, so when we talk about, our bodies are made of matter, our bodies are not completely the same throughout. We have lots of different parts, and so we can pick apart cells in our body and find the different elements that make us up. Elements are arranged on this chart called the periodic table of elements. Now, this is just one periodic table that I found on the internet. If you do a Google image search for periodic table of elements, you will find a lot of different colors, a lot of different sizes, and different numbers within these boxes. Okay, so don't be alarmed. They are all kind of telling you what the organization for the elements is. Okay, this one just has the abbreviation or the atomic symbol for the elements, H, that stands for hydrogen, and 1 is the atomic number. So this chart has just atomic numbers in here, and if we read it top to bottom, left to right, just like we're reading a page in a book, we can see that the elements increase in atomic number as we read across and down on this chart. Okay, so what that means really, as we're going to see, is that the elements get bigger and bigger as we go down. This chart also shows us transition metals, alkaline earth metals. Those things are not really important for this class, nor will you ever have to memorize the periodic table for our fermentation class. It is helpful to be able to recognize some of the important elements by their atomic symbol. You should be able to recognize hydrogen by H, carbon by C, nitrogen by N, oxygen, O, phosphorus by P, and sulfur by S. Those are some of the most common elements that we will be seeing in this class. You'll also be noticing Na, that's sodium, and Cl, that's chlorine, as a compound called sodium chloride. So more on that in a little bit. When we look at the elements around us, we see differences in different substances, and these two pie charts show the relative composition of elements in the Earth's crust, in this pie chart in the upper left corner, versus the distribution and composition of the human body in the lower right. So in both of these, you can see we have something in common with the Earth's crust. The most common element in both of these pie charts is oxygen. Okay? And oxygen is found in its gaseous form in the Earth's crust, inside and between particles of soil. And in the human body, it's found partly as water, partly as gaseous oxygen in our lungs. Okay? And oxygen in the Earth's crust isn't just the air spaces, it also bonds with things like iron to make iron oxides. Then in the Earth's crust, we have some aluminum and iron, calcium, sodium, potassium, magnesium, and other things. Silicon also a big part of the Earth's crust. Silicon is what makes sand look like it's got glass in it. It's mostly silicon material. When we contrast that with the human body, we can see that carbon is the second most abundant element in the human body. And carbon is extremely important for making things like carbohydrates and fats and proteins and making our muscles and bones. So carbon is really big for living things. It's one of the most important elements. Then we have hydrogen, found in various arrangements in the human body, sometimes water, sometimes as a gas, sometimes attached to other things. As a compound, we have nitrogen. Here, nitrogen is found in amino acids making up proteins and muscle fibers. We have calcium and phosphorus, both found in the Earth's crust, and in the human body, they make up bone. I mentioned that elements have their own properties, and some elements are metallic, some are gases, some are liquids, and those refer to room temperature. Now, sodium is shown here. Sodium is one element I pointed out on the periodic table. The symbol is capital N lowercase a, and it looks like a gray metal. Somebody is cutting apart pure sodium right here. Chlorine is a yellowish greenish gas, shown in this flask here. The stopper's in to keep that gas enclosed. But interestingly, when we combine these two elements into a compound, we get sodium chloride, which is table salt. There is an E at the end there, it just got cut off. Sodium chloride is completely different than sodium and completely different than chlorine. Has completely different properties and is stable and safe. Neither of these are stable or safe when they are alone. So we can combine elements to make something completely new. Let's look at the structure of an atom and what we find when we get a little deeper into this. So atoms are the smallest particles of elements. So now we are looking more specifically here at matter. We broke apart matter into different types of matter, elements, and now if we want to look at one piece of an element, we would be looking at an atom. Atoms are composed of three major types of subatomic particles. Protons, these have a positive charge to them, and they're found in the nucleus, or the center part of the atom. So protons, a subatomic part. Neutrons are another subatomic particle found inside the nucleus of an atom, and neutrons are neutral. They have no charge to them. Both protons and neutrons do have a tiny bit of mass, tiny compared to what we're used to, but they make up the weight of the atom. Electrons are the third subatomic particle. These are negatively charged and they orbit the nucleus. So they are floating around outside the nucleus of an atom. And this is what that looks like. This is a very basic diagram showing the positive protons, neutral neutrons in the center of an atom, and then 2 electrons with little minus signs to indicate their negativity, rotating around outside that nucleus. When we document these elements on the periodic table, we often use abbreviations. The atomic symbol, like I mentioned on the periodic table slide earlier, represents the element. So the atomic symbol for carbon is C. That's one that you should know. Carbon is very important for what we study. So what are those other numbers? The larger number is called the mass number. Sometimes you'll see it as a decimal, 12.01 or 12.02, and those are the atomic mass. The mass number, though, when it's a whole number, is the count of protons plus the count of neutrons in the nucleus. So it's similar to the mass or weight of the atom of carbon. The smaller number, or the lesser value number, and I should point out that it's not the font size that I'm referring to when I say larger and smaller, but the value of these digits. The smaller number is the atomic number. And that is going to be specific for each element. It indicates the number of protons found in the nucleus, and that is a very important description of the element. Carbon will always have a 6 in its box in the periodic table. Okay, carbon's atomic number is 6. Now the mass number can change depending on whether we're looking at a heavier isotope. The isotope is an atom that varies in its number of neutrons. So occasionally we'll find carbon that has more neutrons to it, and the mass number would be 13 or 14. But the atomic number never changes. So carbon always has 6 protons in the nucleus, and the mass number is 12 there, so that tells us that it always has, well, in this case, has 6 neutrons in the nucleus. If the mass number was 13, say we had a heavier carbon, the atomic number would stay 6, but the mass number being 13 would tell us that there are 7 neutrons in the nucleus. One way to view atoms is through a Bohr model. A Bohr model is just a simple diagram showing where the nucleus is and where the electrons are for the atom. Now you'll see that the atoms have rings around them. These rings are electron shells. And we're not going to get too deep into electron shells and orbitals, but an orbital is a place where an electron can be located, and a shell is kind of a circumference around the nucleus. Hydrogen is shown there, very simple atom. Hydrogen has an atomic number of 1 and a mass number of 1. So what that says to us is that hydrogen always has 1 proton in the nucleus, and it actually has 0 neutrons in the nucleus. It's got 1 electron that's rotating around the outside. There's carbon, carbon 12, we just talked about, and nitrogen has the atomic number of 7 and the mass number of 14. 7 protons in the nucleus, and there would be 7 neutrons in the nucleus, and this picture shows 7 electrons. The last point I want to make here is that when we have neutrally charged atoms, the number of protons always equals the number of electrons. So the positive charge inside the nucleus will always be balanced by the electron charge, the negative electrons outside the nucleus. This is going to change when we get into ions, but I wanted to point that out. Now, please stay tuned for the second part of this presentation, and I look forward to talking to you.